this would be a very exciting talk. Okay, now we were talking about basically the very same sources that I was talking about before, but from a completely different perspective. So we talked about massive black hole binaries, in the same mass range, in the same more or less regime of evolution, but as gravitational wave sources. And how we're going to, we hope to detect those by means of pulsar timing observations. And I will explain what that is for those that are not familiar with pulsar timing. I just said all of that. Okay, so there were already a couple of talks about gravitational waves, but I want to bring this to a ground floor level, after all the funny things shown by Gary and Steve, and give a very, very simple introduction. So gravitational waves are just a prediction of the theory, Einstein's theory of general relativity, and they are basically waveforms. They are stretch of the space-time that travel at the speed of light. Okay, they have a quadrupolar nature, and they have two polarization, exactly like electromagnetic waves, the plus and the cross polarization. And they are generated by masses with a non-zero quadrupole moment varying in time. Okay. So that sounds a bit tricky, but it's plenty of these kind of things in the universe. So for example, you can think of explosions, like supernovae are exquisite gravitational wave sources, possibly, unless, as long as they're not perfectly axisymmetric, or gamma ray bursts, for example, or rotating asymmetric objects like pulsars with mountains, or but the most promising gravitational wave sources, those that everybody is looking for, are binaries, okay? And there's plenty of binaries in nature, stellar binaries, but those are not very interesting for us. The interesting thing are compact binaries of compact objects. And you have those mass range, you have stellar compact remnants, you might have extreme mass ratio spirals, and Paul told a lot about that. And what is our focus today, massive black hole binaries, okay? Here is just a colorful plot of different waveforms that you may expect from these kind of events. We have a supernova explosion here with a burst of gravitational wave here on the top right. This is some of the waveforms that Steve was showing yesterday from a extreme mass ratio spiral, very rich waveform, which includes a lot of information about the system. And there is a waveform from a merger, by cartoon actually, from a merger of a black hole binary, let's say. Okay. So just to give you an idea of the magnitude of these things, I'm going to bring Steve's approximation to the next level. So for those of you that were suspicious about this approximation of the first order expansion of the perturbation theory, this is my approximation of gravitational waves. So I have two black holes, okay? Separation is A, and the radius of the black hole is R, okay? RG, the RS, the structure radius. Okay, I'm going to linearize the problem, and I'm going to say that the perturbation given by the black holes on the sides of the orbit is of the order structure radius over A. Okay, and this perturbation travels from the structure radius to the observer, that is me at R. Okay, so my age, my strain of the spacetime that I detect is going to be the structure radius squared over sides of the binary over distance to the observer. You put in the numbers, and within a factor of 2, you obtain the exact result. Okay, so this is the strain of a gravitational wave. Okay, very simple, very intuitive. And if you plug in numbers and you derive astrophysical scales, you find that these numbers, unfortunately, are very tiny. And this is why people are trying to detect this wave for the last 40 years without any success, unfortunately, so far, but this will change soon. In astrophysical scales, if you plug in numbers, the typical strain, I'm taking here a binary, let's say, close to coalescence, okay? Very close to the last stable orbit, and I have black hole binaries in my mind right now. This is of the order of 10 to the minus 20 in units of mass, in units of the solar mass, of one solar mass at the distance of the metaparsec, okay? In this case, of course, inversely the distance. And a typical frequency at the mission is 10 to the 4 Hertz inverse unit of solar mass. Now, if you have a 10 solar mass binary at 100 megaparsec, you have this sort of strain at 10, at kilohertz, and this is the typical LIGO ground-based interferometer source. Okay. If you move now to a 10 to the 6 solar mass binary, and you put it at cosmological distance, something like 10 gigaparsec, you have these sort of strains, and you are in the milliards regime, and these are the LISA sources. Okay. And if you go even at lower frequency, and you take a binary like the one Taco was talking about, like a 10 to the 9 solar mass binary, you put it at gigaparsec, you have a characteristic strain of 10 to the minus 14, 10 to the minus 15, and the frequency is in the range of microhertz. Okay? And these are the sources that...
Those are at merger, those numbers at the bottom of there?
Sorry?
And those frequencies, those are at the merger of those sources of those masses?
Yeah, this is the, the frequency is of course less than this, so this is the upper, okay. That would be the frequency at the merger. I think 10 to the 9 solar mass binary, the last stable orbit is 4 10 to the minus 6 or something, the last stable orbit frequency. And those are the sources that we hope to detect with pulsar timing arrays. And maybe at this point some of you may wonder what pulsar timing array is. Not yet. We'll show you this plot first. And this is just the landscape that I just showed you before. These are our sources. This is frequency versus characteristic strain. This is the sensitivity curve for advanced LIGO, for ELISA, NGO, LISA, whatever you want to call it. And this is the discovery space for pulsar timing. This is typical sensitivity curve of the pulsar timing array, and this is typical signal that we're going to talk about in a second. So very massive binaries at low frequency. But what is pulsar timing? Okay, pulsar timing is sort of self-explanatory. Is the art of timing pulsars. Okay. So, and that's my explanation of it. So what do you do? Okay, we all know what a pulsar is. Well, to some extent. And when we observe a pulsar, we have a very precise time tick clock. Okay, that is ticking once per second or something like that. But there is a subset of pulsars which is particularly stable, and those are the millisecond pulsars, the one that ticks several hundred times per second. Okay, and these are the most stable natural clocks we know in the universe. Okay, so what you do when you time a millisecond pulsar, you just take the time of arrival of your pulsar, and then you try to apply a model, okay, to the time of arrival that describes the pulse from when it left the pulsar to your observation. Okay, you assume you have a perfect clock, that's your pulsar. You observe a certain time of arrival. In between, there are all sorts of effects related to propagation, related to the fact that your pulsar was in a binary, related to ISM, etc. And you fit your model to your time of arrivals, okay? And the difference between the two things is the timing residual. So you have a series of time of arrivals, you have a series of time of arrival predicted by your model, you subtract one to the other, and you have a residual. Of course, if your model were perfect, and if there is no noise in your observation, then your residual is 0. Okay, this is not the case because, of course, your observations are noisy, but also because there might be all sorts of effects that you didn't take into account for in your description, as, for example, gravitational waves. And this is where gravitational wave can play. What does a gravitational wave do to your pulse traveling from the pulsar to the Earth? So basically, the very simple way to think about it is like you have a pulsar, you have the Earth, okay, and there is a wave going through. The wave is shaking the pulsar, the wave is shaking the Earth, and you see a sort of, it's like a Doppler effect when I'm talking to you and you're moving away and you're moving back and forth, okay, with respect to me. This is basically what happened. In practice, what happens is that you have a dephase of the pulse given by the fact that which is proportional to the difference of the amplitude of the wave at the pulsar and at the Earth. And when you measure your time of arrival, you have to integrate that dephase over your observation time. And this is what gives you the time residual. Okay? So the time residual is basically the difference in frequency between the intrinsic frequency of a pulsar and the frequency at the time t, given by the fact that the pulsar is moving, integrated over time. And You know that the gravitational wave is a sinusoidal thing. You integrate the sinusoidal thing, you get the sinusoidal thing divided by 2 pi f. Okay, so the typical characteristic residual that you're looking for is something like the strain of your source, and we saw before this is 10 to the minus 14, 10 to the minus 15, over the frequency. Okay, what frequencies we're talking about? We saw before that frequencies are less than 10 to the minus 5. The observation frequency of pulsar timing array is basically defined by your experiment. Okay, you time a pulsar for several years, so the length, the baseline of your observation determines the lowest frequency you're sensitive to, and you time your pulsars once a week, for example. Okay, so 1 over once a week is the upper frequency you are sensitive to. Okay, so the typical frequency range you're sensitive to is between few 10 to the minus 9, 10 to the minus 6 hertz. So microhertz to nanohertz, okay? And if you plug in the numbers here, what you get is that the typical residual of a source of a supermassive black hole binaries of 10 to the minus 4 masses at some 100 megaparsecs is pretty much more or less 25.7 nanoseconds, more or less 100 nanoseconds. It's between 10 and 100 nanoseconds, okay? So this is the time of this is the precision you need to time your millisecond pulsars in order to see something like this. Show you some examples. So remember, the signature is a difference between the gravitational wave at the pulsar and at the Earth, which I depict here with as 2 sinusoid, black and red, and the total residual is the blue curve. So these are 2 typical CPR binaries. If your binary is eccentric, you have some more funny things. And you're looking for something like this in a data set that looks like this. So this is a sample of 17 millisecond pulsars from the Parkes pulsar timing array. And these are the timing residuals where we are trying to look for these gravitational wave signals. Okay. Unfortunately, well, maybe luckily enough, there's not only one massive black hole binary in the universe, but we hope, a population of them. So what you're looking for is not really a source, a signal from one massive black hole binary, but it's a signal from a population of massive black hole binaries, okay? And, well, I'm going to say just here that if you have a population of massive black hole binaries described by a function, which is the number of systems per unit redshift, unit chirp mass, which is this weird combination of masses that is important for gravitational wave emission, and per unit logarithmic frequency, then the characteristic strain of your gravitational wave signal is the integral over redshift and masses of this distribution. Okay? In fact, you don't have a continuous function, but you have a discrete number of sources. So your characteristic signal, your characteristic amplitude, that you just basically replace these integrals with just summations over the sources that you have in the sky. But what it turns out to be is that your characteristic strain goes as the power of f to the minus 2 third. Okay, this is the typical strain of a gravitational wave background from a population of massive black hole binaries in the universe. And the timing residual is hc over 2 pi f, roughly speaking, and so this is f to the minus 5. Okay, so what's the bottom line here is that what we're looking for is a very red signal. And if I take a population of massive black hole binaries and I do a simulation, this is roughly how it can look like. Okay? So in this plot, you have frequency here and characteristic amplitude there. Each triangle is the strain from one source, and this green line here is actually the sum of all of them. So this is the level of your total signal. You see, it's not a smooth background. You have outliers that might be resolved individually, and I come on that in 5 minutes. The thing is that, so this is in frequency domain. In time domain, a signal like this looks pretty much like this. Okay, these are simulated residuals on synthetic array of pulsar. So this is the residual in nanoseconds. I put some white noise, so the total signal is this green spiky curve here, and I put in it this red signal here, which is our gravitational wave background. Aha, that's great, because we see pulsars like that, like this one, for example. So these are timing residuals from a particular pulsar of the Parkes pulsar timing array. And you see this very nice red noise. There it is. The problem is there are all other sources of red noise that can fool you, okay, if you play this game. Because there is pulsar jitter, there is dispersion measure effect, all sorts of things that create this red behavior in the pulsar. But we are not hopeless at this point because all these things are unique to each pulsar, okay? From pulsar to pulsar, you have different sources of red noise. They care about the propagation effect in the interstellar medium, they care about the characteristic of individual pulsars, but you not expect them to be correlated, one pulsar with another, okay? And this is when you win with gravitational wave, because the quadrupolar nature of the gravitational wave implies that there is a specific correlation pattern between pairs of pulsars in the sky. And this was first worked out by Ellings and Downs in 1983. And this is the correlation pattern as a function of the angular separation of two pulsars in the sky. Okay? So if you take a pair of pulsars, they have some angular separation, okay, and you try to detect, and you have a background of gravitational waves. The correlation of the signal in these two pulsars has a specific value, which is given by this curve. And this, by the way, is the theoretical curve, and these are points coming from a simulation of some signal in some synthetic data. Okay. So what you are trying to detect, basically, is this sort of correlation in your pair of pulsars. Okay. So this means that you win by timing many pulsars because you want to find this kind of correlation. And this is what people are trying to do for the last, 15, 20 years. And this is a growing enterprise. There are many people which are involved in this project, and these are the so-called pulsar timing arrays. There are 3 collaborations, one in Europe, the European Pulsar Timing Array, so by surprise. One in Australia, which is the Parkes Pulsar Timing Arrays, not Australia, so by surprise, and one in the US, which is not the US Pulsar Timing Array, because it's actually North America, it's US and Canada, and is Nanograph, North American Nanograph Observatory for Gravitational Waves. Okay, so all these 3 collaborations carry on with their own projects, but they are also united as a big family in the IPTA, the International Pulsar Timing Array. I asked for fireworks at this point, but the organizers did that. And so I said that this is a growing enterprise. This is actually a chart of the papers with pulsar timing array in the title from 1979, which is when this thing was invented, basically, to now. And this is pretty much where the IPTA was created. And you see there is a sort of burst of activity in there. Actually, this is as of June of this year, so now it should be actually much higher there. So just to say, it's a growing field, and there are a lot of people. There are more than 100 people now that are involved in these 3 arrays all over the world. Okay, where am I now? Yeah, the signal. Okay, so we set the stage. We have these millisecond pulsars. We want to cross-correlate signal among pulsars to detect these signals, detect gravitational waves. So now I would like to tell you something about what is the expected signal, how does it look like, and what are the current results that we have. So limits, of course, I'm not telling you we have a detection, and future work, and so on and so on. Okay, this signal here, it turns out that basically depends on, well, you can decompose it in 3 quantities, okay? This end here is the number of mergers that you have. So you sum up h squared, okay? So the value of your h goes with the square root of the number of your sources, okay? So this is proportional to the square root of the merger rate of massive black hole binaries in the universe, right? Then you have a frequency to the minus gamma. And I told you before, this minus gamma is minus 2/3, but this is true only if all sources are circular and gravitational wave driven. And there is no particular reason why this should be true, okay? And I will see, and I show you in a moment what's the effect of dropping that assumption. And then there is the typical mass of the sources. Okay, of course, more massive is are your binaries, the higher is your signal. And of course, these three things depend on all sort of properties of the massive black hole population in the universe. What is the galaxy merger rate that you convert to massive black hole binary merger rate? What is the relation between the galaxies and the host and the black hole? M sigma relation, M black hole and bunch relation, what's the normalization, etc. And then it depends on the local dynamics. So when does accretion happen during the merger? Because if it happens before, then at the merger your binary is more massive and your signal is higher. If it happens on the secondary, more than on the primary, then you are driven toward an equal mass binary, and then your signal is higher again. Okay. So all these sort of things that we don't have a good handle on. And then another important thing is the environmental coupling. If your binary is immersed in a very dense stellar or gaseous environment, then at these frequencies, like a few 10 to the minus 9 Hertz, it can be that the binary still is not decoupled from the environment. So the driving force for the binary shrinking is not gravitational waves, but is the environment, and so the slope of your signal, of your background is different. Okay, having said that, I'm just going to tell you that, okay, you want to estimate this function here, and there are all sort of techniques that you can use to do that. I tried all of them. You can estimate the merger rate from merger trees. You can estimate the merger rate from extensive embodied simulation of structured dark matter formation like the millennium. And you can estimate merger rate from observation, as Richard showed us before. And in particular, I want to focus a second on this work. And what I did here was basically to take all sort of observation regarding galaxy pair fraction and pair counts and the galaxy mass function in the universe from now to redshift 1 point something, where is most of the signal come from. Okay. Then you can combine all this observation with mass black hole host relation, etc., and you can come up with a phenomenological merger rate, a massive black hole coalescence rate, which is based on observations only. And it doesn't, let's say, it fulfills basically all the observational constraints, okay? When you do that, you come up with a range of possible signals, and these are the results, and that I show in these 4 panels here. What you see in this plot are prediction from these models, let's say 1, 2, and 3 sigma confidence intervals where the signal is expected to be. And the dots here are, okay, these were the best published limit as of October 2013, and this is the new best limit from the Australian collaboration that came out 2 or 3 weeks ago, okay? These are different subset of these models. I'm not going into the detail there, but the bottom line is that we are close, okay? So you see that the new limit starts to dig into some of these parameter space. So we are not quite yet where we expect the signal to be, but we are not too far. So it's not unlikely that in the next 5 to 10 years, we might have a detection.
And this is the sort of confusion background, right?
Yeah, this is the average level of the confusion background that you expect from these models. Yeah.
Why the constraint from the current observation is only at one frequency, not at higher frequencies?
Okay, there's a caveat. So this is just something that is misleading, right? Is chosen as just for representation purpose. Actually, this limit here is not a limit put at this frequency. It's a limit that is put at much lower frequency. Okay, and then you translate that limit. So your sensitivity is something like what I'm drawing here with the dot, okay? And then you translate this limit here to the corresponding limit at 1/1 year, assuming a depth to the minus 2/3 power. Okay, so there is that caveat in there. It's not clear.
But why do that? Why not just put it where?
Right.
historical reasons.
For comparison?
Right, no, that's the way, I mean, you're right, it's perfectly, also because of what I'm showing in a second. Okay, so we're not far, which is great news, and I don't see my 5 minutes still yet. No, don't worry, it's fine. No! And, okay, these are some predictions from colleagues in nanograph or about when we might detect gravitational waves. These are, okay, assuming some properties of the red noise, intrinsic red noise of the pulsars. This is probability of detection versus time for 3 models taken actually from this distribution. Where is it? Distribution here. Sort of optimistic, average, and pessimistic model. And you see that they forecast, depending on the, on several things, on the signal and on the red noise, they forecast detection between 2017 and, well, in the most unlikely case, after 2025. But, within 10 years, we have a good chance of detecting something. There is a big caveat to all of that, and I'm coming to this in a second. Yes?
This is just the pulsars we have now with the instruments we
No,
have.
these are the pulsars we have now, adding pulsars at the rate of, what's that, 2 or 3 pulsars per year?
I don't believe these results. So
Okay.
I'm going to,
Sam doesn't believe these results particularly. It wasn't me, it was just.
well, it might be easier to say in what way I do believe. And that's a set of measure 0.
Let's
Okay.
rephrase. Are these too optimistic, too pessimistic, or just wrong?
Way too optimistic, and in some cases wrong, I would say.
You mean this one?
Not even wrong, that's right. So say quality results.
You mean these particular forecasts?
Yeah.
Okay. I have nothing to do with those. Anyway, okay, I showed you before this before, and you have this source in a circle. Because, okay, we are looking for a stochastic background, but it's actually sort of, it's a popcorn noise like a thing, right? So there is a sort of background, but there might be outlier that just pop up, and you can resolve them individually. It actually turns out that you can do that. These are just an experiment that we did, injecting individual sources in a fake array, and the blue things are the injections, and the red are what we recover with the genetic algorithm. So you can in principle do that. And these are current limits actually on the strength of individually resolvable sources with the current pulsar timing arrays. What I show you here, these are the limits using several subset of pulsar. Okay, so we are about 10 to the minus 14. So if there was something up here, we would see it. And you see there are 2 points here. These are actually realizations of a particularly optimistic population of massive black hole binary, I must say. But it's not only one realization. This is a superposition of 200 realizations. So you see that in 200 realizations, we have 2 sources. So let's say 1% of the cases. So it's not quite likely that we have a source at this level, but we are not, say, in a situation where what we can do and what the model predicts are 5 order of magnitudes away. Okay. We're getting closer. Okay, last 3 minutes. 1.5 minutes. I want to talk about the environment. Okay. I showed you before a much simpler formula for the background, much simpler because that was assuming gravitational wave-driven binaries, okay, and circular. But if your binaries are driven by the environment, okay, this is actually the actual, let's say, real formula for the gravitational wave background for binaries. You have this dt in d log nf here, which is the time the binary spent at a given frequency range. And this is different if the binary is not driven by gravitational waves, okay. And here you have all these bunch of harmonics that are given by the fact that your binary might not be circular, but might be eccentric, okay. And in particular, if you have some driving force like, for example, a gaseous disk, your binary would be much faster than if it was driven by gravitational wave only. So you have less binaries at a given frequency, and your signal is going to be suppressed. Same if you have a very dense stellar environment. And also a similar thing happens if you have a very eccentric binaries, because very eccentric binaries emit at much higher frequency, so the lower frequency signal, where we are more sensitive to pulsar timing, also is suppressed. And just want to show you this plot. This is some exercise that I made this year. What I'm considering here is the usual plot: frequency, characteristic amplitude. You have a circular gravitational wave driven scenario here. And what I consider here, I considered some sort of standard models for binaries evolving in stellar system or in gaseous disk. And the red curves are binary evolving in stellar systems. These are circular binaries, and these are very eccentric binaries. Okay, so you see a huge suppression of the signal here. And these are circular binary, but in dense circumbinary disks. And also you see a suppression of the signal there. The problem is that this suppression is exactly where you hope to see the signal, because you're more sensitive to lower frequencies. So the message here is that, okay, the predictions of the models are not so far off with respect to what we can do now, but eccentric systems or strong coupling with the environment may screw you. So hopefully this won't happen, and maybe in 10 years we're going to talk about the detection of gravitational wave pulsar timing. Maybe not. But thanks for your attention. I will take questions.